that concludes the technical portion of the interview. I'd like to perhaps discuss some of the broader implications of your work. And being someone who's very interested in philosophy, um, one of the first things that my mind comes to when looking at your work is that um, I see the lines of like physics and philosophy being increasingly blurred because historically, causality is something that most sciences have simply assumed. And if you do science, you just assume causality, and if you want to examine the nature of causality itself, then that would be sort of in the realm of philosophy. Uh, and I understand that this isn't really like a formal question, but I'd love to hear uh, your thoughts on the subject as to this, I guess, merging of uh, scientific and philosophical thought.
Yeah, so I mean, I come from this background in quantum foundations. I did a degree in physics, and then I wanted to think about quantum foundations. And at the time, this was in the late 1980s. Um, there really weren't many places in physics departments that were doing this. I was lucky to find my supervisor, Ewan Squires, in a physics department, and I was able to do a PhD on in quantum foundations. Now, at that time, the community of quantum foundations was made up really of people from a physics background who were managing somehow to forge a career, and people in philosophy departments. So when we had conferences, we would meet, and that was the nature of the field. And in fact, it goes back to before then. So so you may know that the Nobel Prize just last year was won by people doing research on quantum foundations. So especially doing uh, doing experiments to test Bell's theorem. Um, so John Bell had come up with his theorem in 1964. His theorem showed that quantum theory is in some sense non-local. So even though you cannot signal between two distant locations, if those two locations share a quantum state, there's a sense in which you can't explain these correlations you see as if information had been locally shared. There's something non-classical about this. So it's a very profound result. Um, and so he did that in 1964. And then a few years later, he was approached by a group of people, which included Abner Shimoni, who is a who was a philosopher, and John Clauser, who was one of the people awarded the Nobel Prize this year. John Clauser um, um, did the first experimental test of Bell's inequalities. Uh, and so John Clauser and Abner Shimoni and a few other people, Mike Horn and Holt, were working on making John Bell's uh, theoretical ideas amenable to experiment, actually showing how to do an experiment. Um, and and Abner Shimoni, the philosopher, referred to what they were doing as experimental metaphysics. So this idea that you were trying to test some deep conceptual ideas and you were going to do an experiment to test that. And so that was what led to the first experiment to test Bell's ideas, um, and the Nobel Prize. Um, and so it was this meeting of philosophy and physics. And I think Bell's theorem in particular had a big impact on these communities, and a big impact on my own career as well. So I haven't really answered your question at the level of the subject matter so much as at the level of the way the communities were working and talking to one another. But that continues. So the Quantum Foundations community continues to be made up of people from physics and people from philosophy. We continue to talk to each other. Um, and if you go to a conference, you'll have people from a philosophy background as well as a physics background, and that's great. It means you have a different perspective um, on these same questions.
Yeah. I actually had the pleasure of interviewing a close associate of Alain
Mhm.
Aspect, who was one of the people who won the Nobel Prize this year. Uh, his name was Dr. Serge Massar. I'm not sure if you've
Yeah, yeah, I know him.
collaborated.
Yes, yes, very well.
And yeah, he was telling me about his work on Bell's
Mhm.
theorem, uh, and he actually mentioned your work on Hardy's paradox as a example of quantum non-locality.
Yeah,
So yeah, that's pretty cool.
yeah, 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 yeah. We're
Um,
very much part of the same community. Yes.
okay, yeah, he was actually the first interview I
Oh,
ever
really? Right.
had
Oh, well, that's
at his group.
a good
Yeah,
start.
yeah.
Yeah.
So finally, I'd like to go back to how you reformulated quantum theory, starting from the five axioms. Uh, in mathematics, there are always uh, true statements which you cannot prove starting from the axioms. This is the famous Gödel theorem. Do you think a similar thing could be true for physics?
Yeah, so you sent me some of these questions in advance, and this was the question I was most worried about because I mean, from time to time I've thought about this and I've never really known how to make any sense of this issue. So yes, so there's Gödel's theorem. So which is really just a result in mathematics. You have a mathematical system which of axioms, and it doesn't have to have very much structure. Really, just has to contain the integers and a little more structure. Then you can write down in that system statements which you know to be true, but there's no way of proving the truth of those statements within the mathematical system that you've written down. Okay, so that's um, Gödel's theorem. Um, Gödel always worried that it was just a sort of version of the liar paradox. Um, and I mean, the key statement is a self-referential statement. The key statement that he constructs, which you has to be true by virtue of the way it's constructed, but you can't prove it to be true, is self-referential. Um, so so physics is a bit different. It's not constrained just to the sort of platonic world of mathematical statements. It reaches out into the world. So physical theory, you'd have a set of axioms or postulates, and the job of those postulates is to make predictions about the world itself. Okay, so it sort of reaches outside itself into the world. And so, if you were to search for something which was analogous, like what you're suggesting, then I think what you would want would be some statement about the world which you knew to be true, but you couldn't predict that it was true from the physical postulates you'd written down. So, a statement about the world that was true, but your physical theory couldn't predict that it was true. That would be something like an analogy to Gödel's theorem. And does something like that exist? And I have to admit, this made me start thinking about consciousness. I know I'm conscious, but I also can't imagine how I would ever prove that I was conscious in the context of any set of axioms. However, I also and also the consciousness has a certain self-referential quality to it. Um, but I don't think that quite works as an analogy because Gödel's theorem really, any set of mathematical axioms, as long as they're just have enough structure to include the integers and a few more things, will give rise to this. Whereas physical theories don't have to concern conscious beings. So I'm not sure if that's quite enough, or that's quite analogous. But your question did make me think of that issue. Um, yeah, so I don't really know. I can't think of how you would do it. I can't think of what Gödel's statement you could write down. You could try to construct a statement like Gödel's statement, but in the context of a set of physical postulates. But I'm not sure what that would mean. And so I don't really have a good. I don't have an answer to that question, but I think it's a fun thing to think about. Um, and it's always fun to think about consciousness if it takes you in that direction.
Yeah, definitely. Um, yeah, those were basically all of the questions I had. Thank you so much for appearing on the podcast again.
Right.
Um,
You're very welcome. It was a lot of fun.